Hey, so yesterday we talked about horizontal asymptotes, and then at the end we got asymptotes that were not horizontal and they weren't vertical, and we used the word diagonal. What's another word for diagonal, do you think? I'll give you a hint. Oblique, yes. Oblique means not vertical, not horizontal. It's at an angle. Okay, it's like a slant. It's on a slant. Oh, yeah. Okay? All right, so graph this function using your graphing calculator. Draw a sketch of the function on the coordinate system below. All right, well, let's do that. Now, you will notice that you are going to have to make some decisions about parentheses when you put this in your calculator. Because this has a horizontal line, it is implied that everything on the top is figured out, everything on the bottom is figured out, and then you divide. So in your calculator, you need to put parentheses around the numerator. The reason is, if you don't do that, it'll do -1 divided by x squared, and then it will add the rest of the things. Okay, so parentheses around the numerator, 2x cubed plus x squared minus 1 divided by x squared. Now the next thing before we press the graph button, do you notice how the degree in the numerator is greater than the degree in the denominator? Yep. Now the next thing is, how many degrees bigger is the numerator than the denominator? 1. It's 1 degree bigger. So let's keep that in mind. I'm going to do zoom 6. And there's the graph. Now, does it look to you like there is an oblique asymptote there? Yeah, it does. It does. And does that look like it's a straight line? What's the degree of a straight line? 1. And what was the difference in degrees here? 1. Yeah, interesting. Okay, so I'll tell you what, before we sketch that on the graph, let's see, it would be helpful if we actually knew what that line was. So let's figure it out, and then we'll graph the asymptote and the function all at the same time. Okay? So here's how we're going to do it. We are going to use polynomial long division to rewrite this function as a quotient with a remainder. Okay? So let's do some polynomial long division. Our divisor is going to be x squared. But do you remember when we did the synthetic division how you had to have placeholders? Yeah, well, x squared is the same as plus 0x plus 0. You agree with that? Of course you do. Okay. Now we're going to put the numerator, which is 2x cubed plus 1x squared plus 0x minus 1. Now the reason we're doing long division is because the synthetic division that we know about only works if you're dividing a linear binomial. And this is a quadratic, so we got to do the long. Okay, if you have the setup, here we go. See how there's 1, 2, 3 terms? We want to go 1, 2 over to the third term right here. This is where we're going to start. And we're going to ask ourselves, what times x squared equals 2x cubed? 2x. All right, so let's multiply. Bless you. 2x times x squared is 2x cubed. 2x times 0x is 0x squared. And 2x times 0 is 0x. Put this in parentheses and subtract. 2x cubed minus 2x cubed is 0. 1x squared minus 0x squared is 1x squared. 0x minus 0x is 0x, and drop the negative 1. And now we have to ask ourselves, what do we have to multiply times x squared to equal 1x squared? Positive 1. 1 times x squared is 1x squared. 1 times 0x is 0x. And 1 times 0 is 0. And parentheses and subtract. 1x squared minus 1x squared is 0. 0x minus 0x is 0. And negative 1 minus 0 is negative 1. So this is our remainder, and how we would rewrite our equation is f of x equals 2x plus 1, and then we have to do the remainder, which is minus 1 over the divisor, which is x squared. Okay? So we've rewritten the function as a quotient and a remainder. Okay? Now, looking at this function, what happens to each of the terms as x grows very large and approaches infinity? As x goes to infinity, 2x goes to infinity, right? Okay. What happens to this fraction, 1 over x squared? It gets really small, and in fact, we might as well be equal to 0. And so f of x is approximately equal to 2x plus 1. And that is the horizontal asymptote, or oblique asymptote. Let's go back to our calculator, and let's go to y equals, and on y2, put 2x plus 1. And then check out the graph. Do you see how these tails, as x is getting large, is exactly or nearly exactly that line? So that is the oblique asymptote. So let's graph it. There's the intercept, plus 1. And the slope is 2 over 1, so up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. There's the oblique asymptote, 2x plus 1. And it looks like there's also a vertical asymptote at x equals 0. And so the function graphs like that. Shall we do another one? Yes, we shall. That was a rhetorical question. I didn't expect anybody to say no. I expected everybody to agree. Well, we're going without you then, if you say no. All right, let's flip the page. All right, here is a function, x squared minus 4x minus 5 divided by x minus 3. Before we graph this on your calculator, what do you notice about the degree of the numerator compared to the degree of the denominator? The degree of the denominator is greater than the numerator. By how many degrees is it greater? It's 1, which is linear. So you should expect an oblique asymptote that is a straight line. All right, let's graph this and see what we find out. So parentheses, x squared minus 4x minus 5 divided by parentheses, x minus 3.
Would it be double parentheses in the denominator?
No, because there's only one linear binomial there. You could put double parentheses around it; wouldn't hurt anything, but you don't need them. You'd only need them if there was another linear binomial there, or something else that was multiplied. Okay, zoom 6. Look at that. Doesn't it look like there's an oblique asymptote? Yeah. Yeah, it does. Let's go find it. Let's find it. Okay, so we are going to divide this rational function so that we get a quotient and a remainder. So, this one we could do with synthetic division, couldn't we? I'm going to write it out in long division, and then we can do long division, or shall we convert it to synthetic since we can do it that way? Yeah. All right, so the negative 3 becomes positive 3, and then we use the lead coefficients, which are 1, negative 4, and negative 5. Do you remember how to do this? Yep. Drop the 1 and multiply. Combine according to the signs, and then multiply. Hold it. Is that right? And then combine negative 8. How come this didn't come out 0? Because there's a remainder. Yeah, right on. All right. So we divided x squared by x. So this would be 1x minus 1. Okay. So here's what f of x is going to look like. It's going to be x minus 1, and then we're going to have a minus 8 divided by x minus 3. And so there it is. As x gets really big, what happens to the remainder? It gets really small, infinitely small. We'll call it 0. So f of x acts approximately like x minus 1. And I'll bet that is our oblique asymptote. Calculator time. Go to y2 and put in x minus 1 and graph look at that. Isn't that good? All right. So we can draw a sketch of that. We know that, let's see, the y-intercept is negative 1 and the slope is 1. So there's our oblique asymptote, x minus 1. It looks like there's a vertical asymptote. Do you know where it is, based on looking at the equation? I know it's straight down, that's why it's vertical. But where does it cross? Sorry, that was a little spicy. Sorry about that. Where does it cross the x-axis? At positive 3, the root of the denominator. So 1, 2, 3, there it is. And now we can draw or sketch like that. Is this seeming easier after the second time compared to the first time? All right, well maybe that was kind of a mumble response. Maybe it'll seem easier after we do a third one.
Oh, fantastic.
I'm so excited.
Yes. I love excited math students. It happens so rarely.
I actually did like it something we were doing.
I think this is only hard because of the division. Yeah.
That's what you call computers for.
Yeah, it's so much work. Yeah. All right, let's do another one. Okay, take a look at this. We have x4 in the numerator and x3 in the denominator. Is there going to be an oblique asymptote?
Yeah, there is.
Yeah, and the difference in degree is 1, which is linear, so we're going to get a linear oblique asymptote. Yeah.
I remember the days.
All right, shall we do it?
Is it a good time?
Yeah. All right, so our divisor
Love that pencil.
is
Goblin. Best,
right on.
right there. Best pencil going.
When Mrs. McDonald says it's the best, you know it is. And, Mrs. McDonald, you may not know this, but this pencil is probably 50 years old.
I thought you were going to say it's probably yours.
No, it is mine. It was my father's.
Oh my goodness.
And when my father went through civil engineering school at University of New Mexico, he did a lot of drafting because they didn't have any computer-aided design. And the reason that they have pencils like these are because they have different thickness. You know, there's 0.3, 0.4, 0.5, 0.7, 1 millimeter. And that's for the CAD drawings that you do nowadays where you have different thicknesses of lines.
I had my mechanical drawing class in college.
Yeah, and there are different hardness leads, like H and HB and B.
Still have those.
And the reason for that is you apply the same pressure with the pencil, but the different hardness leads will give you different darknesses. And so you can get with these mechanical pencils different thicknesses, and with the leads different darknesses for mechanical hand drafting. Right. Yep. So that's your historical lesson in what is now done all on computers nowadays.
Oh my goodness.
Yeah.
I like that.
Yeah. So any good draftsman in the day would have a set of these, and they would be color-coded for the different thicknesses and softnesses of lead, so that when you were doing a CAD drawing or a mechanical drawing, that you could select the right pencil. Okay, here we go. Let's do this. X cubed plus 0x squared plus 0x minus 3 divided into x to the 4th plus 2x cubed plus 0x squared plus 0x minus 7. There are 1, 2, 3, 4 terms in the divisor, so we are going to start 1, 2, 3, 4 terms over. We're going to start right there. And we are going to ask ourselves, what times x cubed equals x to the 4th? X. x3 times x is x to the 4th. X times 0x squared is 0x cubed. X times 0x is 0x squared. X times negative 3 is negative 3x, parentheses, and subtract. 0x to the fourth, 2x cubed, 0x squared, positive 3x, drop the negative 7. And you all thought you'd never have to do this again.
I was really hoping.
I hope you're finding out that generally when you've seen something, that I show you something in class, that you are starting to understand that you're going to see it later on or find it necessary later on. All right, next. What times x cubed is equal to 2x cubed? Yeah, positive 2. So 2x cubed plus 0x squared plus 0x minus 6. Subtract 0, 0, 3x minus 1. So that's the remainder. So f of x looks like x plus 2 plus 3x minus 1 divided by x cubed minus 3. That's the remainder. What happens to that remainder as x goes to infinity? You've got a bigger degree x in the denominator. Is the denominator going to grow faster than a linear numerator? Yeah, it is. So the remainder is going to go to 0, and f of x is going to act like x plus 2. And that, mathletes, is your oblique asymptote. Let's check it out. Oh, we didn't do any graphing yet. All right, parenthesis, x to the fourth plus 2x to the third minus 7, close parentheses, divided by open parentheses, x cubed minus 3. And then we said our asymptote was x plus 2. And there it is. There it is. The asymptote is x plus 2. All right, we should do one that's a little more complicated.
Oh boy.
Okay.
I like it.
Yeah, but this is when it starts getting fun.
Okay.
Okay? Oh, we can ask some questions here. Let's do this first. Okay? Based on explorations 1 to 3, what do you think is meant by oblique asymptote? What do you think? What is meant by oblique? Yeah. Not horizontal or parallel, not vertical or perpendicular, what it is is diagonal or slanting. This stuff over here, what it's not is not as important as what it is. So diagonal is really the important answer there. Okay, can you tell an easy way to tell whether or not a rational function will have an oblique asymptote? We talked about it in all three examples. The degree of the numerator is 1 greater than the degree of the denominator. Okay. How would you find an oblique asymptote if given a rational function? Well, what would we do? We would divide the numerator by the denominator, bless you, and the quotient is the oblique asymptote. Because the remainder becomes insignificant. Lastly, must all asymptotes be straight or linear? Well, what we said was to get a linear, the degree in the numerator had to be 1 greater than the numerator. Look at the next problem. I know it's very small, but what do you notice? How many degrees bigger is the numerator? 2. And that's quadratic. What does quadratic look like? A parabola. So what do you bet that we get a parabolic asymptote? Yeah, right on. How about we call it quits for today, and we'll do these ones tomorrow. All right. Excellent.